typically P is very big. And typically we also go and remove the neutral element because we want the quantity longer there. So what exactly we are going to prove in cage? So we have a polynomial. Typically, you have a polynomial of degree t, expressed as a form here, and in general, what we want to prove is basically we actually know a valuation of phi at some point, but without regulating. So that's typically what we do in a cage. So typically, the degree of phi is t here. Then we need two main cryptographic assumptions, which is we need discrete logarithm, basically, which basically means if we have a generator G, so discrete log is basically telling us if we had a G belongs to P and we know a GA belongs to P, finding out A is hard. And then the second assumption we need for KGG from a cryptographic perspective is we need a strong DVM. Which basically means if we know GA and GB, alright, then GAB is basically indistinguishable. So in cryptography, indistinguishable basically means is GAB doesn't really reveal any extra information about the error. So these two cryptographical assumptions. There's one more concept we need in order to work with KGG, which is basically called pairing. So pairing is basically a function that goes from a group, it takes it to basically a represent like that, GD, such that it has two important properties. First one is basically bilinear, which basically means if we have, let's say, x plus y, z, we can basically move these operations any way we want. That's basically pairing. And then the second one we need is basically a non-degeneracy. Which basically means if we have a generator and we apply pairing on it, then this doesn't equal to the ID. Yes. So it will give us some other element to the computation. So these two properties. A lot of times, sometimes you also see these base pair, they are different, G1, G2. So if the G's are same, we call it symmetric, G's are different, and it's asymmetric. Alright, so far, are you guys with me? So for the commitment wise, so can I erase this? So coming to the actual NGT commitment. Basically, we have two important properties, which is basically a binding property, which basically means once you commit, then you can't change. And then the second property, the hiding property, which basically means the commitment doesn't really take the message. So I want to show here the actual flow. Then we can actually just jump into practical. So typically there are three actors involved in KGG. You have a trusted party. You need that for the initial setup ceremony that can generate the public parameters, what we call CRS. And then once you generate the public parameters, trusted party basically sends the public parameters to the prover and verifier. And then prover basically picks a polynomial, and then he computes the commitment of the polynomial, which basically here the generator G raised to the polynomial. And then he sets that commitment back to verifier. Verifier at that time, he basically asks the prover to open the commitment at a random point. So the prover basically computes this particular polynomial. You see what it is. This is sometimes called quotient polynomial or evaluation proof. It's a bunch of things. And then he commits evaluation proof of that quotient polynomial. So when the prover sends, he sends basically three values: the I, the random point, the commitment of the polynomial, and the commitment of the quotient. And then verifier, because of the pairing property, verifier has to basically check the pairing function that he chooses, which was in the beginning. The commitment in the generator is matches this expression. So far, any questions? So one important part is in this kind of setup, this alpha, it needs to be deleted by trusted third party as soon as they generate the public parameter. If somehow the alpha is late, then typically a prover can generate fake polynomial proofs and something. So that will lead to, we just saw the binding property that will be. All right. So what I'm going to do is I'll skip the other parts of it. I'll just practical stuff. I need 3 people. Okay. So you, and maybe Daniel? Yeah? Sure. Good. All right, so you're going to be a trusted third party, all right? And you're going to be a prover and you'll be verified, all right? You're going to pay the baby field and actually compute all these fire field operations and make sure you meet the commitment, the pending commitments. Cool. So I will basically set up the parameters for the field and everything that we need. And I'll walk you through each of them. So you can already derive, so I'll just go through this stuff. So we're going to pick F11 and you just choose addition. So previously when I showed here, this is the multiplicative group. So here F11 basically means our prime order is 11. And we're going to pick a quadratic polynomial, which basically is 2. And we're going to put a generator from our group. So F here is basically F11, 11 is a prime, so 0, F basically looks like this. That's basically the F. So we're going to pick a generator. In fact, in this group, every element is actually a generator. So we're going to pick 2. So trust with third party, all right. You're going to help me calculate the public parameters. All right. So I'll make it easy for you. I'll pick alpha for you. So what we need to do is we need to generate a CRS, a public parameter. It's typically because we are picking a quadratic. We have G, alpha G, alpha. So given G is 2 and alpha 3, I want you to tell me what's the public parameters. And remember, this is F11, so all the operations are modulus 11. Okay? So the easiest way to calculate is you first compute all of the number, you apply modulus at the very end. Okay? All right, tell me. 2. 6. 7. So alpha square is 9 times 2, 18, modulus 11. So that's basically our public parameter. This is basically letters. So in practice, you just don't do this. You actually apply some ABC. Multiple people generate this. And then, so now basically you send this BP to prover and verify. Right? And so I'll also write here the polynomial we're going to pick. So that's our polynomial. So we want to actually prove an evaluation of phi here without revealing So in practice, there are actually multiple variants of KDG. There is one thing called fully open, which basically means the prover actually sends a polynomial to the verifier. We're going to do something called partial open, which basically we don't share the polynomial, but we actually do an evaluation of it. There are other modes of KDG where in the setup you could have multiple, single polynomial but multiple openings, correct? And then another setup is basically multiple polynomial and multiple openings. Because of the pairing properties we saw by linearity and non-linearity, the other two modes becomes quite easy because of the linear dependence relations. So today we're not going to go, we're just going to do a partial. With that, so you are the prover. So we're going to calculate the commitment of phi here at some point. So basically the verifier has to open at some point, and we will choose, like, let's say I is equal to 1 here. So prover has to send, if we go back here, so the prover has to commit the proof polynomial, the commitment, and then verifier has to open at I, and then he computes I, the polynomial value at I, and the commitment of the output. So first we're going to calculate phi of I. So can you tell me phi of I? This is our polynomial, and the point is 1. So what is our phi of I? You plug in here, okay? So 3 times 1, 8 is 15, so 15, right? So the value of polynomial is 1. Doesn't move. So first thing we have to do is to calculate our quotient polynomial, which is psi of x. So what do we have? So the verifier asking us to open at I, right? So let's assume phi of x is like 1. So from polynomials, what this basically means is, if we have a polynomial x and we subtract y, this, if we want to evaluate I, this basically means I is the root of this. So phi of I is equal to y, so we say y, if we have x minus y, the I is a root for this point. Is this clear? From this polynomial. Which basically means that if we have divide this, right, then it gives us some other rational function without any reminder, right? That's what root means, right? Like when you divide two numbers perfectly, there is no reminder. It's very similar in polynomial too. If you divide a polynomial with another polynomial and it perfectly divides, there is no reminder. You just So our polynomial is basically this. So we're going to actually do that. Anybody remember how to divide the polynomials? So we have 3x squared plus 5x plus 7. What is our phi? 4, right? So minus 4 will be 3. And then we need to divide this by x minus 1. You guys remember how to divide polynomials? I'll help you. So basically first we have 3x squared, so you multiply by 3x. So you write here 3x, so we have 3x squared and 3x, so this is 3x. And then you subtract. So we have 8x, and then this is plus 3. And now we have already x here, so we just need 8. So we add 8. This will become 8x minus 8. Right. And then if you subtract, we get this is 11. But we are working in F11, so this is equal to 0. So we have no room. Right? So what we left is basically 3x plus 1. So our quotient polynomial side is basically 3x plus 8. Any questions so far? No questions? Great. So what we're going to do is we're going to calculate the commitment of this, which basically is space. Remember, we have here in the form we have a commitment of CI, right? So the way to do basically is we have a commitment of CI, which is 3, or we're evaluating at what? 3 commitment here. So X becomes alpha G plus 8G. Can you tell me what is alpha G? 6 from our public parameter. This is our public parameter, right? G alpha G. Remember, we don't know alpha. Even though we say alpha is equal to 3, we only use it for generating the public parameter. And after we calculate, we should be here. So when we want to calculate commitment, 3 alpha G plus 8G, we don't know alpha. But we know alpha G from the moment. So this is 3 times 6, 18, plus 8 times 2, 16. This is 34. So this is 3. So the prover basically now sends I, PFI, and the commitment of Q, right? Which is basically 1 phi of y is 4, and the commitment is 2. So this goes to now verifier has
the 34 mod 11.
34
Mod 11.
Oh, yeah.
Should be what? 34.
Oh, yeah. What? Thank you. So the verifier needs to basically now verify if you can verify this, right, given all the data, then that means we have actually quick proof. Yeah. 5 minutes. Okay, I'll do that. So I'm going to erase this, and the verifier has a bunch of information, right? We have I is 1, and phi of I is 4, and commitment is 1. So this one verifier has. Now we need to calculate this expression, right? Basically, commitment V is equal to commitment This is actually very easy to see, because if you remember, our psi x is basically the quotient polynomial, which phi of x times phi of I x minus I, correct? So if I rearrange this, basically what we have is phi of x minus phi of I is equal to x minus I times psi I. Right? So if I take the commitment here on both sides, this side and this side, and apply the pairing, basically I end up with this the commitment of C5, which is basically 4 over there, plus we have commitment coming from phi. This square bracket basically means commitment. And then we have the commitment for the quotient polynomial. And then we have alpha. So if you can verify this, then you know that the proof is correct. So you're going to help me calculate this. All right. So I will erase this, erase this. Actually, this is quite easy because we have all the information that we need. Because we are working with fiber field, the negative phi we don't really know, so we have to basically do a round modulus, turn it to positive. Okay. So phi is what? We have E minus C phi, right, which is 4 here, correct? The commitment of the polynomial 4. And then phi is what? Phi is W4. So we have